Okay, so in this video, we're going to be looking at how to calculate curvature for a function. We're going to look at some examples of parametrized curves in both 2 and 3 dimensions. And then we're also going to look at the special case of a function that is defined explicitly in 2 dimensions. All right, so the curvature formula comes from this idea of taking the derivative of the tangent vector with respect to the arc length. That's the formal definition of curvature. However, calculating this directly is quite a challenge. Converting a function in terms of time into a function of its arc length for most functions is extremely challenging. And if you can do it, then calculating the tangent vector, the unit tangent vector, isn't that bad. But then taking the derivative with respect to the arc length may be another challenge. Now, in principle, if you have a function defined in terms of the arc length, this is relatively straightforward. But we usually don't have functions that are defined in terms of the arc length. And as we actually can see when we do the calculation, this whole process of converting it to the arc length is fraught with challenges in sort of your most generic functions. So there are some alternative definitions for the curvature that will give you equivalent results, but in terms of the time parameter. So one version of this is the derivative of the unit tangent vector divided by the arc length derivative. So that's the derivative of r prime. That's not too bad. Although, again, sometimes finding that unit tangent vector and then doing that derivative again can be a real challenge. So usually I don't use this unless I've already calculated the derivative of the arc length in order to find the derivative of the tangent vector in order to find, let's say, the normal vector. Because that's the other time that you need that derivative of the unit tangent vector. So for our purposes, and certainly for myself, I find that using this third formula with the cross product in it is probably, for most functions of time, the most straightforward in terms of the relative simplicity of the calculations and getting to an answer that, again, is going to be correct, but nonetheless is going to give me the value that I need without crazy chain rules embedded with quotient rules and all that other stuff. So, so even though it involves cross products, it nonetheless is computationally probably the most straightforward for functions of time. And so we're going to look at 2 examples, one in 2 dimensions, one in 3 dimensions. And then we're also going to look at one example where we have an explicit function of x in 2 dimensions and this alternative definition for the curvature for explicit functions in the plane. All right, so let's start with our 2-dimensional case. Mathematically, this one will probably be among the more challenging because the curvature formula is not going to necessarily come out to be the nicest, but it'll give us a flavor of what we can expect. All right, so let us come up with our function. So r of t, and let's do 1 minus t squared and t cubed plus 1. All right, so the first thing we need to do is we need to find r prime of t. And so that's going to be negative 2t and 3t squared. And we're also going to need to find r double prime of t. So that'll be negative 2 and 6t. And so we're going to need to do the cross product. So in order to do the cross product, we're going to need a three-dimensional vector. So we'll just fill in the z component with 0. And recall that our cross product has our components I, j, k along the top. And then we put our vectors in the rows, negative 2t, 3t squared, and 0, and then negative 2, 6t, and 0. Now, when we do the calculations, we're going to readily find that the I and j components in the two-dimensional case are going to disappear. And only the k component is going to remain. And we can verify that the I component would be 3t squared times 0 and minus 6t squared times 0. And the j component would be negative 2t times 0 minus negative 2 times 0. That's just what happens when you have two-dimensional vectors. And in our third dimension, then we get an actual value, which is going to be negative 12t squared plus 6t squared, because it's minus a minus. And so that's going to give us, in the end, negative 6t squared, just in the k component. And so when we take the magnitude of this, according to our formula, we're just going to get 6t squared. And then the second thing that we need to do, of course, is this length of the derivative. And so that's going to be the square root of negative 2t squared plus 3t quantity squared quantity squared. So 4t squared plus 9t to the fourth. And if I want to simplify this a little bit, I can take a t squared out. Like so, and then take the derivative or take the square root of the t squared, and I end up with t times the square root of, sorry, there's no t there, of 4 plus 9t squared. And so if we calculate our curvature, then according to this formula, we're going to get 6t squared divided by this expression cubed and we can simplify a little bit. And cancel out some of our t's. guess we don't want to write it as the square root, maybe. So if I want to find the curvature at any point on the curve, I now have an equation for the general formula for the curvature. And so then I can go ahead and find the curvature at that point. Now, the curvature is related to the essentially how quickly the curve is changing. And so sometimes we think of this in terms of the radius of curvature. And the idea here is that you're looking for essentially a circle that approximates the curve at that point. And the radius of curvature is essentially the radius of the size of the circle that you would need to do that approximation at that location. So now instead of approximating a curve with a straight line, we're approximating with a circle. And the radius of curvature is approximately 1 over the curvature. So in this case, we would say that the radius of curvature is again, the reciprocal of our curvature. So if we consider, for instance, what the radius of curvature is when t is equal to 1, we're going to end up with 1 times 4 plus 9 to the 3/2 over 6. And if we plug that into an equation, what we can do is we can find the radius of curvature at this point. This is not a great number, but nonetheless, we want it to intersect with the curve at the point where t is equal to 1. So that's not the center of the circle. That's where the circle approximates the curve. And if you experiment a little bit with this exact value, which is going to be 13 square root of 13 over 6, and you try to find a circle with that radius and position it so that it approximates the curve at that point, you do actually get something that looks like it makes sense. Here is our circle with the given radius, and the point that we're approximating it at is t equals 1, which is actually going to be at this point right here where we're on the curve. And you can see that the circle does, in fact, do a reasonably good job of approximating this curve at the point 0, 2. Now, let's continue with our example with a 3-dimensional example. And we will look at a helix, because helices generally will simplify relatively nicely when we calculate things like the arc length. So let's think about, let's do 4 cosine t, 3t, and 4 sine t. So this is wrapping around the y-axis. And so we're going to need to find r prime of t, which will be -4 sine t, 3 and 4 cosine t, and then also r double prime of t. So -4 cosine t, 0, and -4 sine t. Now, if we do our cross product, we'll go snag the formula again. We're going to need this one. And so we're going to need our cross product. Oops. So we've got -4 sine t, 3 and 4 cosine t, and -4 cosine t, 0, and -4 sine t. Now, these are not all going to turn out to be 0 everywhere. Because we're in 3 dimensions. So let's think about our I component. That would be these two. So that's going to give me -12 sine t minus 0. And then in the J component, I'm going to get, it looks like 16 sine squared t. Minus a minus will give me a plus 16 cosine squared t. And then in the K component, I'm going to get 0 minus a minus 12 cosine t. And this middle term is going to simplify a little bit. 16 sine squared t plus 16 cosine squared t. If I take out the 16, sine squared t plus cosine squared t is 1. And so this whole thing goes away. Now I need to find my magnitude. And so that's going to be the square root of, well, 12 squared is 144 sine squared t plus 16 squared is 256 and 12 squared is 144 cosine squared t. Oops. And if I take out the 144 from my sine squared and cosine squared, then this will become 144 plus 256 is 400, which is equal to 20. So my numerator is a constant. And if I find the magnitude of r prime of t, then that is going to be, that's up here. So 4 squared is 16 sine squared t plus 3 squared is 9 plus 16 cosine squared t. And I'm basically going to do the same trick. I'm going to take my sine squared and cosine squared. I'm going to take out the 16. Sine squared and cosine squared are going to be 1. And so I'm going to be left with 16 plus 9, which is the square root of 25, which is 5. And so my curvature is going to be equal to 20 divided by 5 cubed. Which is 20 over 125, which is going to be, if I cancel one of the 5s, 4 over 25. Now, this is a constant, and that should make sense. If you think about the shape of a helix, it's always curving at basically the same rate. So there's a constant curvature. And so at any point along the curve, you can always approximate it, as we've seen in the previous example, with a radius of curvature that is always also constant. It just has to move along the curve. Now, the last example we're going to look at is with a function. And so let's just think about some common function. Let's say x cubed minus x. So x cubed minus x is going to have a repeated root at 0, and then it's going to have another root at 1. So it's going to look some, it's going to go up, it's going to go down, it's going to go back up again. So our formula for the curvature in this circumstance is going to be this one. So we're going to need to find f prime of x, which is going to be 3x squared minus 1, and f double prime of x, which is going to be 6x. And then in the numerator is we're going to have the absolute value of 6x, so that it's always positive. If we put in a negative x, we should still get a positive value for the curvature. You can't really have a negative radius of curvature. And then in our denominator, we're going to find our magnitude of the arc length, essentially. That formula is still the same, but it's just expressed in different terms, and then we're going to cube it. So let's just look at this guy. So that's going to be 1 plus 3x squared minus 1 squared. And if I FOIL that out, I'm going to get 9x to the 4th minus 6x squared plus 1. And so 9x to the 4th minus 6x squared plus 2. And so my formula is going to become the absolute value of 6x divided by 9x to the 4th minus 6x squared plus 2 to the 3/2 power. And as we did before, we could evaluate this at some particular value and then get some radius of curvature. Obviously, if you plug in 0, you're going to get 0 because that's actually a critical point. So the function is changing direction. We could do it at another value. Let's say when x is -1. So kappa of -1. And then this is where I pick -1, so the absolute value would actually apply. So it's just going to be in the numerator, it's not -6, it's just going to be 6. And then in the denominator, we're going to end up with, well, -1 to the 4th is still 1. So 9 minus -1 squared is still 1 minus 6 plus 2 to the 3/2 power. So 6 over 9 minus 6 is 3 plus 2 is 5. To the 3/2 power. And then as before, the radius of curvature would be the reciprocal of this.